Hey everyone, welcome back. You know how we love to geek out on the future of tech here, right? Well, buckle up, because today we're going smaller than small, like seriously tiny, to explore the world of additive nanomanufacturing.
We're talking about building things atom by atom.
Exactly. It sounds like something straight out of Star Trek, but believe me, this is real science, and it has the potential to revolutionize electronics as we know them.
It's a pretty big deal.
You even shared a fascinating article with me about this, and it dives deep, and I mean deep, into the science behind it, specifically a process called laser-based sintering of nanoparticles.
Yeah, that's the heart of it, how we take these insanely tiny particles and fuse them together to create something completely new.
Okay, so nanoparticles, we're talking way smaller than a grain of sand, right? Like microscopic even.
Way smaller. Think billionths of a meter.
Billions. Wow, okay, so we're talking seriously small stuff here, and that's where this laser comes in.
Exactly. This isn't your average laser pointer, by the way. We're talking about a super precise tool that can manipulate these nanoparticles with incredible accuracy.
It's like a microscopic welding torch, fusing these tiny particles together to build. Well, what exactly can we build with this technology?
The possibilities are pretty much endless, but imagine flexible circuits that can be printed onto anything, even biodegradable materials.
Wait, biodegradable electronics. So no more mountains of e-waste. That's incredible.
It's one of the really exciting applications of this technology, making electronics more sustainable.
So we've got these nanoparticles, we've got our laser, but I'm guessing it's not as simple as just zapping them together and calling it a day, right?
It's definitely where the science gets really interesting.
That's what that paper you sent me is all about, right? Molecular dynamics simulations. To be honest, I took a look at it, and it's pretty dense, even for me.
I can imagine. It's not exactly light reading.
So break it down for us. What are these simulations, and why are they so important for understanding this whole process?
Imagine being able to see how individual atoms interact with each other during this sintering process.
Like having X-ray vision for the nano world.
That's a great way to put it. And these simulations allow scientists to do just that, giving them an unprecedented level of control over how these materials behave.
So it's like a virtual laboratory where they can test out different scenarios before actually building anything in the real world.
Exactly. And that's crucial because when you're working at such a small scale, even the tiniest detail can make a huge difference.
So we've got these incredibly powerful simulations that let scientists see what's happening at the atomic level. What are some of the challenges they're trying to solve with this technology?
Well, one of the biggest is figuring out how to control the sintering process. You see, you can't just point a laser at a pile of nanoparticles and expect them to magically assemble into a smartphone.
I was kind of hoping it'd be that easy.
Wouldn't that be nice? But seriously, there's a lot that can affect how those nanoparticles fuse together. Their size, for one.
Okay, so we're talking about the size of the nanoparticles themselves. How small is too small, or is there a just right?
Well, both actually. Smaller nanoparticles tend to sinter faster because they have more surface area, which means more contact points for bonding.
That makes sense. More contact, stronger bond.
Right. But it's not just about individual particles, it's also about how they're arranged, how they come together.
So like if they're all jumbled up versus neatly aligned.
Exactly. Scientists call this misorientation, and it plays a huge role in how well the particles fuse. Think of it like building a wall with bricks. If the bricks are all slightly tilted in different directions, the wall won't be as strong or stable, right?
Makes sense. A crooked wall is not a good wall. So what's the solution? How do you get these nanoparticles to line up perfectly?
Well, that's part of what makes these simulations so powerful. They allow scientists to test out different variables, like the angle of the laser or the temperature, to figure out the optimal conditions for getting those nanoparticles to align just right.
So it's all about finding that sweet spot, the perfect combination of factors to get that perfect bond.
Exactly, and it gets even more interesting when you start talking about different materials. Because not all nanoparticles are created equal, you know?
Oh, right. I remember reading in the paper something about silver being a better material for sintering than copper. Why is that?
It comes down to something called cohesive energy, which is basically a measure of how strongly atoms are attracted to each other within a material. Silver has a lower cohesive energy than copper, meaning its atoms are a bit more willing to break their bonds and form new ones with their neighbors during sintering.
So it's kind of like silver is more easygoing, more willing to go with the flow and bond with whatever's around it.
That's a great way to put it. And that seemingly small difference in atomic behavior has huge implications for how these materials perform in electronics.
It's amazing to think that something as tiny as an atom can have such a big impact. It's like a whole new world of engineering, but on a completely different scale.
Absolutely. And we're just beginning to scratch the surface of what's possible with this technology.
It really is mind-blowing when you think about it. We're manipulating matter at the atomic level. It's like something out of science fiction. But the thing that really got me was how scientists can actually predict how these nanoparticles will behave during sintering.
Yeah, it's not magic, although it might seem that way.
It's that equation, right, the one in the article, equation 4.
That's the one. It's actually a pretty elegant equation when you consider what it's doing, predicting something called characteristic sintering time.
Okay, characteristic sintering time. Break that down for me. It sounds a little intimidating.
It's actually pretty straightforward. Think of it like this. You're baking a cake, right? You need to know how long to leave it in the oven at a certain temperature to get that perfect golden brown and make sure it's cooked all the way through.
Okay, I'm with you.
So characteristic sintering time is basically the same idea, but for nanoparticles. It's the amount of time it takes for those particles to fuse together completely at a given temperature and under specific conditions.
So instead of preheating the oven to 350, scientists are figuring out the exact laser settings and time needed to bake their nanomaterials.
Exactly. And being able to predict that time is a game changer. It takes out a lot of the guesswork.
It's like, before this equation, it was like trying to bake a cake by just throwing ingredients together randomly and hoping for the best.
Exactly. This equation gives scientists a recipe, a way to optimize the process and get those nanoparticles to sinter exactly how they want them to.
Which is crucial when you're talking about building electronics at such a small scale. I mean, we've talked about flexible circuits and biodegradable electronics. What else could this technology be used for?
The possibilities are pretty much endless. Imagine super efficient solar cells, ultra-fast transistors for next-generation computers, even targeted drug delivery systems.
So we could be seeing this technology everywhere, from our phones to our hospitals to, well, pretty much everything.
Absolutely. And it all starts with understanding the behavior of those tiny nanoparticles.
This deep dive has been incredible. It really makes you appreciate the power of nanotechnology and how these tiny particles have the potential to create a huge impact on our lives.
I completely agree. It's an exciting field to be following, that's for sure.
Well, that's all the time we have for today's deep dive. A huge thank you to our expert for joining us and sharing their incredible knowledge. And to all of you listening, keep those minds curious, and we'll see you on the next deep dive.